I am an operations engineer with 42 Lines. It's a software development company that does some operations work. We've been working with Fitbit for a number of years doing some operation visibility tasks. And today I'm going to talk about scaling the log aggregation pipeline that they use, kind of a long and torturous journey that we went down. And I'm hoping to save other people some of the pain and suffering that we experienced. So what is ELK? Obviously, there's the moose jokes, but it's a series of interesting scaling bottlenecks that we had to deal with. The traditional pipeline for ELK is you install a Logstash or a shipper agent on your hosts. They send to a broker queue of some kind. Logstash, again, picks up from the broker, indexes into Elasticsearch, which is a wrapper around Lucene, and then the Kibana node, or the Kibana server will then query that data to give you a web interface for it. When we started 18, 20 months ago, we were running about 35,000 logs a second, trying to keep a week, but we were down to 6 days of retention because of memory issues and other things that were happening. We are now running a steady state of 150,000 logs a second, peaking at 220,000 or so, and we're keeping 30 days of retention. So we've gotten much, much bigger, especially having this all in a single cluster behind a single pane of glass for developers and analysts and QA and whoever else needs to be able to search any of it. Capacity planning suggests that we need to be able to hit 300,000 a second sustained in the next 12 months and be able to burst to at least 400,000 logs a second, which is kind of ridiculous in some ways, but it's where we need to go, and that's what the business needs, and so we're building it. Our current tested peak throughput is about 350,000 logs a second. We had a cluster stall recovery, and we were able to benchmark it at that point to actually see what we could do at this point. So we're close to where we need to be, ahead of the game, which is really kind of nice. But as I walk through the architecture today, you can see why and how we're scaling the pieces of this. I should take a side note here. This is for Fitbit, but this is not tracker data. This is not step counts. This is not elevation changes. This is none of the health data at all. We don't keep any of that in the system. This is only firewall logs, application logs, those kinds of things. We don't want to have the PII stuff in here. We don't want to have all of the HIPAA things you have to do a lot of extra compliance work for. This is only for developers and people to look at the code that we're doing and watch releases and look at historical security events and not deal with tracker data. Also, before I start, there's 3 basic kinds of search that you need to be aware of. And if you were only optimizing for one kind, you can build a single cluster with a single kind of hardware, a single tier of stuff. But there's 3 kinds of search. There's your standard release monitoring, where developer releases a piece of code, and you want to see right now, are we still in business? Are things working? Are exceptions spiking? Are we getting 200s or 500s? However that works. There's the looking at the trends, historical surveys of the last week or 2 weeks, and saying, what does traffic look like this week versus last week? Did we actually resolve that code issue? Is that exception class falling? Those kinds of things. And then you have the very specific deep dive into, okay, 2 weeks ago on Thursday, we had an issue with something, and I want to go back and look at what happened, do a post-mortem about it. And these have very different performance characteristics and very different use patterns. And if you understand how your users use the data, you can build a better service and a better cluster for it. So in the beginning, we were using the very traditional setup. And yeah, so 35,000 logs on average, peaking at about 45,000. But we were limited to about 55,000 logs a second at our maximum throughput from a stall recovery. And we knew that wasn't going to scale, and every week, every month, every year, we're getting more and more data coming into the system. So we started looking at, and then the cluster itself was a relatively small cluster. We had the node counts here. We were using Redis as our broker. Redis is really kind of nice in many ways, but we had to move off of it for reasons I'll get to in a little while. Some of the initial problems we had were the field data breakers will happily estimate the size of a request in terms of memory cost, but it's an estimate, and it can still sneak through and have things run out of control. It also doesn't do CPU cost or disk I/O cost, so it doesn't actually know how expensive it's going to be to read the data off the disk, or if it has to do analytics or regex parsing of the data, that gets really expensive really quickly. Elasticsearch has its own cluster protocol, protocol, and it's a fixed 30-second timeout, and it has 2 retries. So if you garbage collect for 150 seconds, you're done. You're out of the cluster, and you have to restart and rejoin, and if killer then comes in, you have all kinds of other issues that you have to deal with. And then, of course, you have the issue where a user does a heavy query trying to find some complicated top-end sort or something, and that now stalls indexing because the same resources that are writing your incoming log data to disk are also being used to query that same data. And the facet searches in the older versions of Elasticsearch are expensive and they're memory intensive, and they don't take advantage of any of the new doc values or the other pieces that really help with performance and efficiency going forward. We had further problems that our HA proxy logs are coming in at such a high rate that we couldn't keep the TCP sockets clean, so we were sending them over UDP. And that was mostly working, but it was still too high, so we had to start dropping all the non-error messages. So all the 200 series stuff we just dropped. It was only going for a week, so we just decided that the performant thing we needed was when there's errors, when there's redirects, that's what developers really need at this point, and we couldn't keep up with the full board traffic. And doing a lot of regex parsing and a lot of other parsing on logs gets really costly very quickly. And so we were trying to figure out the best way to move forward with all of this. And then as a side note to that, when you have MySQL logs, sometimes MySQL will dump binary into your logs, and that doesn't play well with anything else. So you have to then regex parse out the binary. That is a particularly awful nightmare to try to figure out and do. So change is the only constant. This is kind of the guiding principle with what we're doing, and we started looking at doing a larger cluster. The business folks wanted to go to 30 days of retention, so we have 4 weeks of data. Because of looking back over about a week, we could have 2 sprints, and you could say, okay, the developer released a piece of code, something didn't go right, we fixed it quickly right now, we're gonna look back on it in a little while and know that the data will still be there when we want it in a little while. We were bringing more hosts on, we wanted to bring more hosts in to send data in. We wanted to bring in a lot more types of logs that people were saying, oh, well, there's a lot of value in these other audit types or these other things. We want to get the MySQL slow log in. So we started bringing in more different kinds of data, which required more parsing and more rules and more other pieces. And there was a very strong desire to stop dropping all the 200s. We wanted to ingest all of HA proxy, which was going to bring up our traffic volume significantly. And then the stated design was, okay, we wanted to handle 2 years of growth with the ability to burst occasionally to 2x our normal ingestion for whatever happens. But that's kind of that was our basic design goal. So we built, because we can't name things and naming things is really hard. The first cluster was ELK and the second cluster was ELKO2. We decided to replace Redis with Kafka because everybody seems to be using Kafka these days and it's pretty awesome. Instead of having a single kind of data tiers, instead of having a single data node, we had 2 different categories of hardware, so we could separate search from indexing. There was also a desire to start archiving all of our logs to S3, so we had long-term log retention instead of just having the window that was in ELK itself. And then we also wanted to start analyzing the Kibana query logs, because that gives you a lot more insight into how the users are actually using the search that you're doing and how they're utilizing your service. So the basic design, I'm leaving out the shipper side of it, but Kafka would dump into indexers that would read off the Kafka stuff, and then they would write into the cluster. And this works fairly well. We had the masters, we had the read-write nodes for indexing, and then we had a read-only tier for the long-term storage. We like Redis a lot. Redis is pretty awesome, but probably because it's operationally very simple. There's no clustering, there's no quorums, there's no other pieces. It comes up very quickly and very easily. You run out of memory, it's very fast. Unfortunately, Redis has a number of issues that were blocking us on things. As Logstash on the fleet was sending to Redis, if the Redis queue got full for any reason, if the cluster wasn't indexing the data, the Redis queues would get full and then stop, and then all of the Logstash shippers would back off. And you had no idea how much data was waiting on the fleet to come in. So once you resumed ingestion, you didn't know how long it was going to take to clear your backlog before the developers could get back to work on release monitoring and other pieces. Furthermore, because it's just a simple queue, you can't have multiple consumers of the Redis queue. You have to, once you've consumed the data, you have the data and you're done. And we were doing this in memory because for performance reasons, and standing up more and more single points of failure was not going to be a good idea. So I guess last year we started looking at Kafka, and we have a Kafka-shaped problem. This is actually a perfect use case for it. It gave us incredible visibility into what we were doing It let us segment log types by topic, so we can say, okay, if there's an HA proxy problem, it's not going to impact the application logs or syslog. All these things are now separate, and we can individually reconsume or send pieces other places. It gave us fault tolerance, and it's very performant even on SATA. So when you fall out of your file system cache and you're reading off the SATA drives for Kafka, we only see about a 20% hit in read performance, which means that we can still operate happily. If we need to re-index off of 12-hour-old data, we can do that, and we don't fall miserably behind. It also allows us to have multiple consumers of the same data, and this is really important going forward. I'll hit back on this a couple of times. But this is a really nice piece of the puzzle to have solved for us. Do you remember your garbage collection tuning? When Kafka garbage collects, if garbage collects too long, you suddenly lose all your partition ownership and things get a little wonky, but it's not been that bad. I do have all of this in notes on a GitHub page, so you guys can see these tuning options. And this is what LinkedIn recommends. Use G1GC, use a recent version of Java, and these settings get us to, well, where we are now, which is hundreds of thousands of logs a second, and it works very nicely. So, I'll wait for the picture. So the hot worm architecture was a new concept last summer, and now it's becoming old hat, but it's the idea that you have a search tier that has all of your historical data, and you have an indexing tier that brings in new data. And if you remember back to the kinds of search, release monitoring really cares about what happened right now. It cares about what happened in the last 30 seconds, the last minute, because you're trying to watch for new errors and new conditions that are coming up. So the hosts that are handling the indexing are overspec'd pretty wildly for I/O and CPU, so they can handle both of the tasks of indexing the data, writing it to disk and not stalling when that happens, and letting people do intensive, short local queries on that data. Yeah. And once you move off of the release monitoring queries, once you get into the historical surveys and you get into the historical incident stuff, performance requirements drop significantly. You no longer need ridiculously fast returns on search, especially when you're doing I'm looking at 3 weeks of data, and I'm looking for a pattern of access stuff. If it takes 2 or 3 seconds to load the graph, nobody complains. That's an acceptable use because you're not usually doing things that are really latency sensitive. So for cost-saving measures, because we're trying not to spend all of the money, we decided to use spinning disk for that. And there's a caveat to that later that was really awful, but I'll get to that as we go. And then once you do hot worm, it's really easy. You tag your nodes with some kind of identifier to say this is a read-write or this is a read-only node, and then you issue a JSON call to your master, and you say, hey, I want to retag this index to that node, and the cluster picks everything up and moves it around for you. It's really quite handy. And so this is this is from a while ago, watching the tiers move around, and data scales are on either side of the graph. But you can see at night, during our low point of user search, we would then migrate the data around. We also wanted to bring in our Kibana query logs. Just 1 second. So Elasticsearch has a slow query log, and Kibana has its access logs. And we had little visibility into how users were using the system and the kinds of queries they were issuing, especially when you're doing a top 10 sort on an analyzed field. So it's actually going through and scanning all of the data on a very high cardinality set of data that's all unique. It's very expensive memory-wise, and it runs things out of memory very quickly. But when you're doing this, be careful of logging loops. Early on in the process, I was looking for a memory condition in Elasticsearch, and so I had an extra piece of Logstash configuration that when there was a memory error, it incremented a counter for me and added a log. But then when I searched for that memory error, it considered that a hit, and it just started looping, and that was not so much fun. So be careful of that one. But once you have this, you can see what the users are doing, and you can understand why they're trying to access the data, and then you can go talk to them and say, hey, this would really be better suited if we did aggregations instead, or if we change the data type, because this isn't the right kind of data for the kind of search you're trying to do. Yeah, so it helps us to diagnose problems. I do apologize for the wall of text on all of this. So here is our Elasticsearch grok pattern. It's pretty standard. It pulls the Java logs apart and gives us our Elasticsearch message. And then this doesn't actually render, unfortunately, because the type is too small. There's a GitHub page, again, that has all this code in it. Can you read the bold at all? OK. So one of the things the slow query log gives you is the time range of search in 3 different formats, of course. But if you pick that apart, you can then work out the number of minutes in the query range. So when you're looking, you're having a query problem or you're having other issues, you can look at people going, OK, that was a 15-minute query, that's a 15-minute query, that's a 30-day query. And that was not so good, those kinds of things. It adds a lot of flexibility to things and lets an administrator very easily see when there are any issues that way. The other piece of this is we want to do long-term archiving. So we just use another Logstash tier that reads off Kafka, writes to disk. We compress the files as much as we can because we're trying to save on transit, we're trying to save on S3 costs, because again, we're trying not to spend all of the money. And then we AES encrypt it and push it up to S3. And if you're going to do this, look into standard IA, the infrequent access log type, because it'll save you about 40 to 50% on your storage costs, which is kind of handy. And once you get past 90 days, most people aren't looking at then you're going into legal discovery, which has its own cost equations. And that's not the same thing as this. Some of the pieces that we hit with this, unfortunately, were window sizes. Logstash has or had, at least at the time, a fixed TCP window buffer. And if you have a high latency network, this doesn't play well, and you will be constrained, and you won't understand why, because you'll forget about bandwidth delay product, which you learned about 20 years ago, and you haven't thought about in the last 5 years. But it's pretty nasty, so pay attention to that one. But again, change is the only constant. We were told to expect spikes of up to 2x. And here's typical 5-day indexing for us. We were running happily at like 85,000 logs a second. Everything was good and rosy. And then this happened. This isn't a spike. This was a hard doubling, and this was over a longer time period. We went dramatically up, and we kept it all. And because there was some internal communication issues that happened that I wasn't told that this wasn't going to be a spike. This was actually a sustained doubling for this particular event. And we started to scramble because we could handle the indexing side of this, but we hadn't sized the storage tiers for this kind of thing immediately. So the new thing. 6 months after we built ELKO2, we started building ELKO3. And we had a couple of different design goals, and a lot of this came into how to scale each piece of the stack by itself without having to then rebuild a new cluster the next time, because rebuilding clusters is not a fun process. And we think good notice is 3 to 6 weeks at this point, so the developer says, OK, we're bringing a new service online. We're going to add 50,000 logs a second to the system. OK, well, thank you for telling me. Let's figure out what we need in terms of other capacity, other planning for this. Part of the reason you need to do this is you need to limit your cluster node counts as you're building stuff. You want to limit the impact of a shard failure or index failure or a data center rack goes down or whatever it is. You want to try to contain your failure domain. And also the developers wanted to get on Kibana 4 on newer versions of it, and there were some performance and memory efficiencies that came out of Elasticsearch 2 that we wanted to move up to. So this was kind of our opportunity to move to that. Because ELKO2 was still running happily. It's just we knew we were time limited in how long we were going to run into a wall with it. And again, Kafka lets us have multiple consumers running off the same data stream. So we'll just set up another cluster, and we can keep ELKO2 as our live system, build ELKO3. Once it's ready and we have 30 days retention, we'll just switch over. So this was the new format. We have Kafka feeding into a bunch of indexers. They feed into the multiple clusters that we're running for ELKO3, and then the Kibana nodes look into this. And all of this is made possible by tribe nodes. It's a special kind of Elasticsearch node that's actually a member of 2 clusters at once instead of just 1, which means that it has some drawbacks, but it's a full member of the cluster. When you ask it for data, it actually returns the aggregate set of data for the node counts and the shard counts and other things. But it also means that if you query it for data, you get the combined result set for everything back, which is extraordinarily helpful and solves the problem of trying to scale out the search side of it and lets us keep everything in a single pane of glass for all the developers and all the users of the system to have one place to go for all their logging needs. So the reason you need to limit your node counts is Elasticsearch is a full mesh. Every node makes and holds open 13 TCP connections to every other node in the cluster. And when you have 200 nodes in your cluster, you have tens of thousands of connections. If you look back at your network latency stuff, if you have a change to the cluster, like you create an index, you move an alias around, you do other pieces to this, all of the nodes in the cluster have to acknowledge every change. And if you don't acknowledge it within 90 seconds, you get kicked out of the cluster and things start to get bad for you. But those time limits are there for a reason. You don't want to have stale nodes that have old data that have other pieces. You need to keep your cluster size contained as best you can. So now we can build out kind of pods of the ELK cluster, join them with Tribe, and we have a scalable solution that doesn't involve building ELKO4, ELKO5, or ELKO6 relatively quickly. So I have that set up incorrectly. Our original plan was to build the clusters with kind of this balance where we had 30 indexing nodes and 80 storage nodes, but we realized a little later than we should have that we had over-provisioned the read-only tier significantly because of the way memory works. There's an Etsy paper about scaling ELK, and they talk about the actual memory allocations. I don't have it in my slides here today, but look into that and read up on it if you're trying to figure out your scaling limits, because you'll be surprised at how many documents you actually can pack into these nodes. We also moved to a shared indexer tier. Instead of having an indexer tier per subcluster, we decided to have a pool of indexers that wrote to all of them. And Elasticsearch 2 is pretty awesome. The APIs are better. It's a lot more stable. The cluster communication is better. You get to use doc values, which is really awesome, because Kibana 4 uses doc values, and their doc values basically, instead of doing in-memory searches and heap searches, you can trade disk space for heap, and then you have a lot less out-of-memory issues and a lot less underruns when you're doing sorting fields and stuff, which is really great. And the Kibana releases, unfortunately, are tied specifically to versions of Elasticsearch 2, so you have to kind of upgrade them together. There are also some opportunities about Elasticsearch 2. The biggest being that the field names that you use can no longer contain periods at all. It'll fail to index, it'll drop the document on the floor, and you have a bad day. And a lot of people use Java class names for field names or other things, and so suddenly we had to go through and do a lot of very heavy lifting. Elasticsearch doesn't support Kibana 3 because they changed their search type. They changed it a long time ago, but they finally deprecated. They finally dropped the facet search. And so a lot of developers were really happy with Kibana 3, and Kibana 4 is a very different product. So it was interesting getting all of them over and using the new system. And also, whenever you go from a major version to a major version, you have to do a lot of just testing, and there's a lot of really painful time spent trying to make sure the crash recovery works as you expected, and all the other settings that you're relying on still operate the same way, or at least similar enough to the same way that you have to keep up with. As we were building the ELKO3 cluster, we came into another interesting piece, and this is why we're actually not at 1 trillion logs on disk right now. It was decided that there was an internal tier of application servers that were logging mostly superfluous, or not superfluous, they were logging things that we didn't actually need all the data. We needed to know the health of the service, we needed to have a representative sample, and we wanted to keep user requests threaded all the way through the system, and so, but we wanted also not keep all of these logs. So how do you do that? How do you keep only specific user requests and be able to drop that way? And it's pretty easy, actually. At the load balancer, you put a UUID of some kind, as long as it's globally unique. And then every time you pass the log to the next piece of the chain, you make sure that the application server, or whatever it is smart enough to say, okay, well, I'm going to take this out, I'm going to put the request into the next field, and you can pass it down. And as long as it's unmolested, this process will work for you. This is also in the code in the GitHub page. So we can stick it in with a murmur3 hash, because murmur3 is memory and CPU efficient, and it has a very wide distribution across the key space, so it's very even for this work. And then we just do a stupid hack to convert it to a float from 0 to 1. So we can use percentages later instead of trying to remember which size int we're using. And then we drop logs. We can drop logs based on the consistent hash, and this way we always retain the entire portion of the request that we have. So if we have the sampled log entry, we have all the rest of it. We know we have all the rest of it without having to worry about, okay, well, we have an entrance from one thing, and then the next piece in the stack is from a different request. And we can change the sampling rate as we go via Puppet, and that works out quite nicely, actually. Apply this sparingly. Don't just think this is a magic bullet that will get you through some kind of scaling issue, because developers and business folks and help desk and everybody else who uses the system expects to see certain patterns and certain levels of logs. And if you don't clearly communicate to them beforehand that you're changing the scaling metric, they're going to think either there's a lot less traffic or there's a lot more traffic or other things have happened. So you need to be careful when and where and how you do this. Ideally, just stick another field into your index to say, hey, when this log was processed, our sampling rate was at X. So then it's really easy to programmatically, when you're building a dashboard, to say, okay, well, my sampling rate was X at the time, so I need to scale by 9X, 8X, whatever it is. And all this can be done via Logstash, which is kind of handy. The consistent hashing stuff let us also build a disaster recovery cluster very, very inexpensively, because it just drops 99% of the data. But otherwise, it is, and so we run it with less than 10 hosts. But it has the same version of everything. It has the same configurations of everything else. It uses the same pipelines. It's a hot running disaster recovery cluster that isn't the cold standby that a lot of people do, or the powered off, God forbid, where you have to then bring it up and remember all the things that have changed and all the other things that are happening. So if there's a disaster, we increase the sampling rate, we add more hardware to it, and then we're back in business. So that's a really handy way to do this. And then in the event, when there's a disaster that actually occurs, you have a baseline of logs. It's going to be a representative sample of a very small amount of logs, but you can see at least trending in patterns immediately. So you're back in business as quick as possible. The reason why you can't use dots is because of the way JavaScript or the way JSON works. So in this example, foo is both a top-level object and a string field, and Elasticsearch doesn't like that. There's a ddot plugin that they shipped that is extraordinarily expensive on CPU. 2x is the best case, actually. It's really not intended for production use. It's more for getting you through the transition. I was going to talk a lot more about this until 2 weeks ago when Elasticsearch announced that in 2.4, there's a flag that turned dots back on. Okay, that was unexpected. There are some caveats to that. If you're going to turn dots back on, they have a couple of different ways to do it, so you need to be very careful with your data formats and how things are working. So read the docs. I haven't actually turned this on yet, so I can't speak to that directly, but it's there now. Another issue that came up with the new system with Elasticsearch 2 is that shard relocation stopped being you just put it on the task queue and get to it whenever you can, to being, this is an emergency action, you need to evacuate the node right now, which blocks the task queue for everything else you're doing. And if you're moving 1,000 shards, suddenly everything else that you're trying to do, like a mapping update or an index creation or anything else that you're trying to handle, also blocks and waits. And if it takes 2 hours to move all your shards around at night, well, suddenly you can't do anything else for 2 hours, which also means you can't node join, you can't node leave, you can't do a bunch of other really important operational tasks. So we're starting to break our indexes into smaller and smaller pieces so we can interrupt this less. This was a surprise in the 2x stuff. It's not bad, it's just it was different behavior. So it's making sure you understand what happened. We're also using Mirror Maker reasons. We had to put our production cluster in a different data center, which had a higher latency link. And so, great, Kafka has Mirror Maker. Mirror Maker works really well. Everybody else seems to use it as well, and people seem to love it. It has a couple of peculiarities to it, but it's good. But guess what we'd completely forgotten about? So this is what happened to us. On the graph at about 17:15, latency started climbing on the network link, the backend network link. And we usually were handling about 35 milliseconds. And it got to 120 milliseconds, and then kept on climbing. And by the time it got to 250, we were done. There was nothing flowing through the system anymore. And everything was healthy. The systems were all happy. The systems were, okay, what's going on here? And it was because our socket size in the Mirror Maker was, again, statically set. And that came back to bite us again. Bumped up the socket buffer, and we're back in business. And about 160 is now where our limits are for transparent replication. But that also impacts other pieces of the stack, so it's not just the logging infrastructure that starts to hiccup at very high latencies between data centers. The final major craziness that came out of Elasticsearch 2 is that they implicitly assume SSDs on everything. And SSDs are great, I love them, but when you're building storage nodes with as much data as we're doing, they're really expensive. It's going to basically bring up the cost of our cluster by about a factor of 3. And Lucene doesn't support leading wildcard queries, but Elasticsearch kind of hacked it in. Unfortunately, when you issue a query with a leading wildcard, it can't use the inverted index anymore, and it can't use a bunch of the other pieces. So it actually goes through and scans every field of every record looking for a match. And if you're using a spinning disk, this is an absolute nightmare. We have 330 billion documents in the cluster, and if you did a leading wildcard search, one of the things you could be searching on is timestamp. So it didn't even care what time window you were looking at. It just said, oh, we're going to walk through everything now. And I mean, we're going to walk through everything. And that was really awful. So on your SSD set, you go from a half-second query to a 5-second query, and that's not good. We had the worst issue of this. It took 12 hours to literally read every field of every record on disk. And of course, because all the nodes are now completely pegged to the wall, you can't do anything to them because they won't acknowledge cluster changes, and now you're stuck. Digging through, I found this setting, and it actually works remarkably well. You throw this, you restart all your nodes, because this is a runtime cluster setting, and a user does a leading wildcard search, and it pops up a red banner at the top saying, you can't do that, it doesn't work. And as long as you've correctly set the analyzed or not analyzed and indexed and whatever on your field set, the tokenization that they're expecting to work actually works. So instead of searching for star.gmail.com, you just search for gmail.com, and they get what they're looking for. But they've been trained by Google and other places that, you be star.whatever. Well, that's not how Lucene works. So this just prevents that from happening. This was really nasty for us and made us really question our sanity for a long time until we found what was actually going on. Yeah, and then that's the other part, is when you have clusters of hundreds of nodes, restarting everything is not fun. Again, tribe nodes to the rescue. So you have half your data is in one subcluster, half your data is in the other one. You can now restart one of them and leave everybody up on the other one, so half the data is available. People can still do patterning searches. They can still look for history. And indexing now flows to the other cluster entirely, so release monitoring still works. So that helps. It's just still kind of painful to have to restart everything. These are a couple of other important settings that we found as we were running through this. So the leading wildcards, the balance threshold is how it's deciding where to stick the shards of indexes on the various servers. And if you have a lot of shards, like 30 or 40,000 shards, and you have hundreds of indexes, and you have hundreds of nodes in your cluster, it will take forever. It'll take 6, 8, 10 hours to try to figure out exactly the right optimal balance. So you just push it up from 1 to 1.1, and it's a little less balanced, but our data rolls off at 30 days anyway. So it's fine to have slightly out of balance nodes for us. The index buffer size stuff is for when you're doing your indexing nodes. You want to reserve a lot of memory for the index buffer to keep that pipeline running quickly. And then, of course, the mlock all true, because you don't ever want to swap with this, because it's bad. Badness. So that's the end of the talk. The link on the bottom is the GitHub page that has all of the code examples and the actual slide deck on it. So if you need to look at stuff, it's there. Feel free to shoot me questions. I'm happy to talk about this. I've been doing this a lot for the last 18 months, and I'd love to commiserate with people on it. Questions?
You were talking about when you were switching versions, there was a lot of testing to be done, and you have a target of 400,000 logs a second.
Yeah.
How were you simulating that kind of data load to verify that you could do that before you actually rolled it out?
So there's a lot of extrapolation you can do from, you bring up a node and you run a generator on it to just dump a lot of data into it, or you say, I'm resetting my Kafka offset to 24 hours ago, and just read as fast as you can. That gets you to a single node performance approximation, and that's really helpful, but the only real way to do it is when we were restarting all the nodes for the leading wildcard flag, it was a perfect time to say, okay, well, what can we actually push through half of the nodes? And we were able to easily handle the full indexing load currently on half the data nodes we had right now, so we know that we can run both of those in parallel.
Sure, thank you.
Yeah.
Hey, thanks for your talk. Definitely can commiserate with you. Running Elasticsearch is brutal.
Yeah.
One of the problems I've encountered is like when you need to do an upgrade of, or just a simple like, I want to upgrade the configuration even, not even versions, or I need to do an OS patch or something. Like, what kind of strategies do you have for deploying that with a zero downtime upgrade? And how long does that take you to do that kind of deployment process?
Well, again, by having the tribe nodes, we can take portions of the stack down and then divert all indexing to the other nodes. So we stop the indexers that are feeding into, say, ELKO3A. And so all the load's now going into B, and all live search and all release monitoring goes in there, so we don't block a release by doing that. We then take down the masters on A, so no cluster changes will happen. We stop all the servers, we apply whatever updates we need to apply, we bring everything back up, and then we switch the indexers over to only writing to A, and then we do B. We have a couple of test servers that we use, and then we also have the DR cluster, which we upgrade first. It's kind of like a final staging environment to make sure that there aren't any unexpected hiccups at low volume. You can't actually test the high volume stuff other than doing it in production, which is kind of unfortunate, but we do the best we can. And luckily there haven't been that many like really critical Elasticsearch security issues that have come up in the last year, so we haven't had to deal with that too often.
So end to end, how long does that usually take you?
So I've done a full restart of both sides. I want to say it was 5 hours, 6 hours. And during that time, at least half the data was always available. So it wasn't a service outage entirely, it was just portions of the data were not available for search at that time. So,
thanks.
Yeah.
As far as the flow of the logs from the clients up to the Kafka server and mirroring and all that, is any of that over SSL, or do you have any, I guess, what did you do as far as secure transfer?
So we're still using Kafka 8.22, I think, which doesn't have SASL, doesn't have SSL, doesn't have Kerberos. We're currently evaluating the performance impact of moving to SASL and Kerberos and SSL and stuff in a 0.9 or a 0.10 release. Okay. But I've been helping another group internal to Fitbit with upgrading to Kafka 10, so I'm kind of watching that process to know what we need to do for the ELK side of things. But at the moment, it's just the 0.8 connector, which is, there's no SSL on it, unfortunately.
Okay, are the clients using FileBeat, or what are you using on the clients?
So for most of the hosts, we're using Logstash installed on the fleet, and we let Logstash try to do the heavy lifting in terms of grokking and parsing, and the server that generates the log is responsible for transforming the log into JSON, and then it dumps the JSON into Kafka, and then the indexers pick it up, and if there's any final processing to do, we'll do it there. One of the nice things you can do with this is you can actually have Logstash emit metrics to statsd or to graphite, so you can have live counts of log data about types of logs or exceptions or other counters flow into your metrics platform at time of index, or at time of pickup from the fleet rather than at indexing time. So this gets you around the issue where if there's a stall in indexing and now you're behind, you're not trying to then stuff into statsd that's at the wrong timestamp. So do everything on the client side. With Mesos and things, we're trying to go really lightweight, so we're using FileBeat there. But it has a number of caveats itself where it just basically emits, it's a JSON blob, but I think it only has 3 fields, and it takes the entire message and just sticks it in one of them, even if it's a JSON message, which you then have to re-parse later. So that's kind of fun, but.
Okay. And as far as access to Kibana, even though it's an engineering team, obviously there's logs that, like the internal Elasticsearch logs, you probably don't want, everyone doesn't care about that. Is there anything you're securing within access to the logs among the team of people that can access the server, or is it just openly, like the open source Kibana, you just all go and share dashboards and everything?
So we have an interesting layer of access stuff coming in. So Apache, we're actually double proxying with Apache to get our Kerberos authentication tokens into the log so we can correlate users and searches and other things. But once you've authenticated to the system, there is no data in the system that is so sensitive that nobody else can look at it. There is some discussion of having a separate ELK cluster for security, not trying to do multi-tenant, just have a separate cluster for them, because they have some logs that they're interested in that we're not currently ingesting into this, that it would make sense, but it's it's a different kettle of fish. So it's a shared pool for everybody.
And actually, one more. So 30-day retention, I mean, we struggle with how long people want logs, and some of it's because they have a dashboard and they want to just see the metrics, which we were trying to figure out if there's ways to sort of take snapshots of the metrics and dashboards, or to allow to have, more historical information without the actual logs. I guess it's, or deciding subsets of logs that they really care about longer than others. I mean, is there any games you've done with that besides just extending all logs?
So we have, because we index into a bunch of different indexes, HAProxy and Tomcat and syslog and other things. And you can set different retention rules for different indexes. Like our QA indexes, I think, drop at 14 days because that's not usually as critical to look at for longer periods. And people can search for 2 years, but they're only going to get 30 days back. And the 30 days was picked because it's 2 sprints. You'll always have the last 2 sprints in there, and that works.
Okay, thank you.
Absolutely.
I'm kind of wondering, as an organization, how you deal with the costs associated with additional logs that go into the system. Because obviously there's a cost in building a logging system that's this secure. In your previous iteration, you disabled HAProxy for those 200 messages. So how do you go about determining that cost or getting approval? Is that,
So
speak on that?
we try to provide as much capacity as we can for as little price as possible, just because we're not in the business of building big shiny things for the sake of building big shiny things. That's not why any of us are here. We're trying to deliver some kind of value to either a user or a customer or whoever it is. And as much as I like building a big shiny thing, like I was really thinking we're going to be at 1 trillion logs on disk for this talk, and we're not. And that's actually a great thing because it means there's less cost and there's less overhead and there's less management. And my pride isn't even hurt by not doing the big crazy. But we don't have fine-grained cost accounting for, this team is generating this many logs, and so they're going to get, internally cost accounted for that kind of stuff. We haven't done that. We haven't needed to. It's been, if you need the log, log it. If you don't need the log, turn it off. And we try to be clear with the developers that basically you control all of this. Our logging increases are generally not tied directly to user traffic. It's tied to Kafka comes online and somebody misconfigures a producer, and suddenly they're dumping tens of thousands of logs a second into the queue. And we have to go figure this out and deal with it. Or they really need a debug log about something. And so that brings in a lot of extra logs for every request that comes into the site. Okay, well, we need it. There's a valid reason for all of this stuff. So we haven't had to turn the screws on the cost accounting yet.
Okay.
I'm hoping we don't have to, because that's another whole mess of administration that isn't so much fun, but
Okay.
yeah.
Thank you.
Yeah. Anybody else? Okay. Thank you, guys. Appreciate it.